In 5.2, we're going to introduce definite integral through areas. So remember that area of the rectangle is height times base, height times base. Such a simple idea, and surprisingly, it becomes so important in calculus class and in general in the understanding of this whole concept. Then we defining the Riemann sum, and now you know what Riemann sums are. Those are sums which will be working heavily in calculus 2 class. The sum f is taking at some kind of point. And this point this time will be called x sub k star instead of just x sub k times delta x. Delta x, do you remember what delta x is? Step size, width also, right? So depending if geometrical point of view, it's width, or I would call it base of each rectangle, and also step size. Delta. Okay, also, do you know, did I ever mention this called delta? Just for you to know. And this is a sigma sum notation. So base times height. This is what we did with those rectangles. When you multiply base times height, you get area of one rectangle. And then you keep changing the counter. K is the counter. If you already code, you know very well what counter is. Dummy variable or just an integer counting from 1 to n. So I'm adding up all the rectangles from 1 to n. Sum means adding up all the areas, and it gives you approximation, left, under approximation, over approximation, and so on. And we learned that we have left Riemann sums. You don't have to write this down. We already know. Right Riemann sums. And here's the idea. This time we're not going to be just looking for the graph below the areas, for the area below the graph. We will be looking below, above, and so on. So if in red is my function, and I want to approximate the area below, I remember we could use, for example, left rectangles. Here they are. Find the area of each, add together. But how about above the graph? Let's do the same thing. Left endpoints keep touching the graph. So the difference will be that whatever are above will be positive and whatever below will be negative. Thus, that's example of the Riemann sum, left Riemann sum specifically. And we're talking about the graph of the function 1 minus x squared, so it's parabola, part of the parabola. Thus, if the function is very, very below x-axis, then the result will be negative. And if it's very, very above, the result will be positive. So in this case, we can guess it will be negative because negative parts are bigger. And you either approximate it or you actually calculate it, and we're going to be doing that. So you already wrote down the net area. The net area is, so here's the perfect idea here. This is the amazing idea. You see those empty pieces? That is missed gaps. So that's underestimation because the missed pieces are still there and we never calculated them. And then do you see those extra pieces in here? That's overestimation for you. We don't like that either. So I would like it to have a perfect, nice estimation. This is when you have many, and now I can actually show you that, many rectangles filling it up, all the space. So let me show you. Area below graph, rectangles. And by many, I mean instead of 8, I think in that case it was 8. Can I have a 100? Can I have 1 million? Well, if I'm going to 1 million, why not to have infinitely many then? So let me show you. That one is kind of boring. This one. The more I have, the better the approximation is. Is the internet so slow today? Just open it, don't be shy. Okay, here you go. The more rectangles you see, the better the approximation is. This is the example of the left endpoint touch. So if I want to have 1 million, that would be nice. 2 millions will be even better. Infinitely many will be even better. And I'm talking about area below and above the graph. So this is a nice example with sine and cosine. Why not to have them so many that it will just satisfy that the area is exact, not approximated. How to have infinitely many things, though? That's a weird mathematical idea. Look at this. Lots of gaps at the beginning. So area is calculated at the bottom. And then the more I add, the more perfect it becomes. And at some point, it covers everything. The rectangles become so thin that they just have a line. So the width of each rectangle shrinks to 0. And number of rectangles expands to infinity. Exactly. And that's why we learned limits. Well, not just for that one, but limits has lots of applications. So that is why the definition of net area and definite integral, let's do it here. Definite integral has limit in it. Write down integral, a nice stretched S sign, remember, that's integral sign, make it beautiful. You see they even do like little loops at the ends, which is nice. From A to B, usually we put A below and B above. Some books type it like this, but internationally it should be below and above. Of f of x dx. So the part inside is called integrand. We know that already. Integrand. I think D. Somehow I forgot right away. So someone should check it in Google. Is it D or T? The grammar problem. Integrand. And we're integrating it from A to B with respect to variable x. And the definition is, it's a limit when, in this case, they say delta goes to 0. Put delta x, that is better notation. Delta x shrinks to 0, limit of what? Of sums of all of those areas. Infinitely many areas. There's two ways of describing it. Let's do with n going to infinity. There are two ways of describing it, and I like this one better. Areas are not infinitely many. It's still n, but n will go to infinity. So if you have infinitely many number of rectangles, let me write this down. This is number of rectangles. Then they will be so thin that the area, let me briefly show you here, that the area will be covered not with rectangle anymore, but with a line, and it becomes beautiful and perfect. So that is the idea. You can describe it in two ways. Either you have infinitely many rectangles, or it will be infinitely small with respect to width of each rectangle. So both are definitions, correct definitions. So what are we doing here? Height times width, step size, where x sub k with a star is not left endpoint and not right endpoint. It's a random one. So to be honest, we don't have to make it always left, right. We can do random one. And math still works because it still adds up all rectangles, and there are infinitely many of them. And that is the definition here. Here's nicely explaining it really well. So you can write down the second definition too. Delta x, I would at least do delta x, goes to 0, and here is delta x. Delta is fine, but it's kind of mostly used in upper level classes. So b is the upper limit of integration, a is the lower limit of integration. Oh, here it is, it's d, I was right. Inside of the integral we have integrand, that's the one we are about to integrate. Then upper limit of summation, lower limit of summation, and then sums. We're summing the sums, no, we're summing areas of integrals. That is the idea. And then delta, if you want to keep it the way they have it, delta is a step size. Step size. And also it's a width. Width of rectangles. And they don't have to be the same in general calculations. Math will still work out fine. But when they're the same, it's easy to do by hand. Width of rectangles. So here's the idea. And then to explain you some English behind this, a function is defined on the closed interval. It's called integrable if it has an integral. Here's a definition of an integral. This limit should exist. Remember, not all limits exist. Left limit must be equal to right limit, right? So exist. It's unique over all the partitions. Partitions means those sub-intervals. They can be different sizes, actually. So we don't have to have the same width. And all of the choices of x sub k star. So it doesn't have to be in the middle. It can be on the right, completely on the left. It can be somewhere random. This limit is called the definite integral of f from a to b. And that is definition. You don't have to write this down. Here is nice explanation. The variable of integration called the dummy variable. That's the official terminology. I mentioned it last week. So it's variable that is completely internal to the integral. You can change it. So as you can see, the area is the same below this graph. You don't have to write it down either. That is just nice to have notes. The area is exactly the same. The area is an object. It's like feet squared, meter squared, whatever it is squared, right? So it's a physical object. That's what area is. So the number will be the same, 5.7 everywhere, for example. But you can write down f of x dx, f of omega d omega, f of s ds. And who remembers my favorite? From A to B, f, who remembers my favorite? It's the first letter of my name. F of j dj, because dj is funny. See, good job, remember. That's my favorite. So it's called a dummy variable for a reason. Because in general, you can just change it the way you are. The answer is the same. Functions are integrable if f is continuous. So let's write this down. F must be continuous on the closed interval, bounded. So it cannot go to plus infinity or minus infinity. Or it can have breaks, but there should be a finite number of the breaks. So it have to be or bounded with a finite number of discontinuities. So it can have discontinuities, but it should be not infinitely many of them, and it's still bounded there. Then f is integrable. So you see, continuity was a very important definition. Continuity comes from the limit existing and f, this hole filled in where the limit is pointing. That's the beginning of this class. Continuous functions are important. Lots of laws of practical physical properties are coming from the continuity. And now we're going to learn this. Net area. You already wrote it down, but net area is integral from A to B, which equals, I have my own notation, positive area minus negative area. So it says area above x-axis minus area below x-axis. The area below x-axis called negative area. So sketch this graph. That's like a very nice way of actually we have a specific example right now, so you don't have to sketch the graph. I only have it in your notes anyways. So area number 1 is positive. Area number 3 is positive because it's above the x-axis. Area number 2 is negative. So total area will be area 1 minus area 2 plus area 3, like so. And as you can see, this function is not continuous. And that's what's interesting here. The function has a jump, and one more jump over here, and even a hole. Oh, actually, it's filled in, it's fine. But it's a finite number of jumps, so the area still exists. It reminds you of roofs of several buildings, and maybe a basement. So if you ask if there's an area of discontinuities functions, yes, they are. This is a building. So it totally makes sense. And in this chapter, we're going to ask you to find those areas using geometry, even though you might know how to do it using fundamental theorem of calculus. No, in this chapter, they ask you to use geometry. So let me see, like so. I want to do this. Oh yes, I wanted not to reveal the answer yet. Let's do together a simple example with triangles. So a simple example is, we have, let's find integral from 1 to 6, 2x minus 6 dx. And finally, we're getting into the whole idea of definite integrals. So people who took this class before probably know how annoying it is that we know how to do this fast and easy, but they want you to review geometry. Step number 1, sketch the graph. Here's the graph. This is y equals 2x minus 6. Either use graphing calculator, or my way of sketching the graph is choosing 2 points for a line. When x is 0, y is minus 6. When x is 3, y is 0. So I know it's going to go here, goes through 0, continues. So you only need 2 points for the line. And now, the second thing to notice is, do you want me to find the area? Infinite area? Because it goes infinitely to the left and right. No, they say from 1 to 6. So that is my A and B. That is what fixes the interval. So I only need it from 1 to 6. And this is where the areas showed up. One area is below the graph, below x-axis, and the other area is above x-axis. That means one will be negative and the other will be positive. And usually we call them A1 and A2. Here's my line. So I will call it A1, A2. Total area will be minus. It's kind of doing this. So there are two ways of seeing it. Yeah. Total area is A1 plus A2, where A1 is negative. So either you do A2 minus A1, or you add them up together, remembering that A1 is negative. Well, that's the idea here. How do you do that? Using areas of triangles. Do you remember the area of triangles? Here you go. Look at this. Julie prepared everything for you. Triangles. Exactly. Half base times height. Right? Trapezoid. We will have that in this chapter. Trapezoid. Trapezoid is like partially, bless you, it's partially a rectangle. So we do have width times height. So you take the base h and then multiply by a plus b, two parallel sides, and then find the half of that. And here's your geometric formulas to review. So we hope you remember that. And now you find the area. Area 1 plus area 2. Area 1 is area of the triangle. Still, I feel like which one is better. I guess I would say let's do minus area 1. Yeah. So it's going to be minus, and now I'm creating the area 1. Area 1 has height 4, width from 1 to 3, 2. So 4 goes below x-axis, and that's why it's negative 4. And that's when I'm trying to figure out how to explain. Even though it's negative 4, we see it as a distance, right? A distance is 4 units. So it's going to be 1/2 times 4 times 2 for the first triangle. Plus, and then the second triangle is over here. The width is from 3 to 6. That is 6. So 1/2 times 6. And the height is from 0 to 6. 6. And you have 4 and 9. But remember that the one below the graph is negative, so it becomes negative 4 plus 9. And the answer is 5. The final answer has to be positive. Actually, no. The final answer tells you which area dominated. If the bigger area was above the x-axis, the positive hill is bigger than the total area is positive. But if the pit or a canyon was having a bigger area, then the total will be negative. So this number tells you some information. So does it make sense? What do you think? How interesting is that? And also, I wanted to ask you this question before we move on. Question: what is going to be the area of the same 2x minus 6 dx? Okay, people who know this, don't tell it right away. I want to see if people can understand it if they never saw that before. But this time, I want it from 1. We had it from 1 to 6. I want it from 1 to 1. What is the area if I have the beginning here at 1 and then the end here at 1? What do you think? What is the area of that rectangle triangle, that line. What's the area of that line? From 1 to 1. 0. Can anyone explain why? People at the back, do you know why it's 0? So it is 0. It is correct. Very good. But why? We're going to have definition of definite integral later. Again, it will definitely show up from definition of the fundamental theorem of calculus. But even from the limit, let's see. The limit takes widths and heights. What is the step size? The step size is 0 from 1 to 1. What's the size from 1 to 1? It's 0. What did you want to say? What did you want to say? What did you want to say?
Oh, I was just going to say it's 0 because you're starting at one point and finishing at that exact same point, so you're not doing anything.
Yeah, like what kind of area did we cover? There's height to it, but width or the step size is there's no step size, it's 0. That's why multiplying by the 0 width. 0 times height, and then you add them up together, it gives you 0. So no step size, no area for you. Same with any other from 3 to 3, guess what? 0. And that takes us to the properties. Yes, to the properties of the definite integrals. You're supposed to write it down if you want, but I provide you with this nice table, so to be honest, your choice. And let me walk you through. Those properties are fun. I actually think students usually like it. Both functions are integrable. It means they have an integral. Integral from a to a is 0. There's no width, like I told you. Even the very hard one, and you'll be happy to see it on some kind of homework or exam. Sine, logarithm, arctangent of cosecant. From 0 to 0, from a to a, it's 0. Doesn't matter. Sometimes you want to flip the order. From a to b becomes to b to a, and vice versa. Yeah, you can do it. Just put negative sign. Because it's still the area. It's just if you go from right to left, you change the way you're counting it. So change the sign. That is also comes from the definition. That's why it says definition there, because it comes from the definition. If you have two functions add up or subtracted, you can calculate two different integrals, just like we had with integrals before. And then I always like to explain it. For this problem number 3, there's a proof. Some students ask me about it. It comes from the limit. Limit of sum is limits of two sums. Each sum becomes part of each limit because functions are continuous. Each limit gives you definition of each definite integrals. From the area point of view, here you go. Here's the function. I'm looking for the area from here to here. Well, guess what? I can write down the integral just... there are two different functions. I'm talking about different property. I can find the integral for one function first and then another function after that. Boom, I have two integrals. So it also comes from understanding of geometry. Constant c, kick it out or put it back. We have that before. And the fun one is the breaking point. From a to b, what if there's a nice point, p, where you're like, it would be nice to just find this integral first and then this integral after that. Can I do that? Yeah, those are areas. You'll still have area 1. It's just going to be from A to a new point P. And then it's going to be from P to a new point B. So here it is. It's a gluing point. So sometimes I see it like this. You can glue it back together from A to B. It's glued out of two integrals from A to P, P to B. If everything is continuous, why, or just integrable, why not to do that? So here's your idea. As you can imagine, some areas, some functions has infinitely many areas. Sines and cosines, look at this, how cool is that? Infinitely many areas. And now it depends on where and how you calculate it, but actually you could calculate them separately, A1, A2, A3, A4, and then you notice that some of them are the same. So why not to calculate all the top ones and all the bottom ones and be good with that? Nice. Do you have questions about this? Does it make sense? It's like the beginning of new kind of chapter. Even though it's 5.2, it's the beginning of the chapter. So it's kind of interesting. I have them again here. I have no idea why. And now let's do the example. let's evaluate the integral in terms of areas. And here's your integral with the absolute value. Oh, you will think about it like, why did they put absolute value there? My life is already stressful. So yes, let's learn how to work with absolute values in other areas. This chapter, people stuck on this chapter mostly because of the geometry. Post your questions in the forum and we play with it together, but I also solved many of them. I solved many of them in my videos just to play with geometry and show students that you should not forget geometry classes. So, step 1, you understand what is in front of you. Integral from 0 to 10 of the function absolute value 6x minus 1, and those parentheses are not necessary there. Why they put them there if it's already absolute value? Dx. That means the function inside is f of x. Step 1, you can sketch it first. Sketch f of x. F of x is, I don't know, do you know how to sketch absolute values? From pre-calculus class, you should. Do you know? Yeah? Let's try. So I see first a line. Here it is, 6x minus 1. I quickly make a table. That's my way of doing it. You don't have to. At 0, it is minus 1. At what? Anything else? What?
1 by 6.
Yeah, but then 1 by 6 kind of hard to find, I guess. But yeah, good point. 1 by 6 is 0. So at 0, it goes a little bit down. And then at 1/6, it is 0. Here's the line, right? Here's the line. And they want to find it from 0 to 10. That's quite far. That's like over here, I guess, 10. And here you go. Check it out. I have it. Here you go. This is your area. It's like a very, very tiny gap over here. It doesn't start from 0, 0. And then you build this graph. I used GeoGebra or any graphing calculator. Yes?
Wouldn't it be positive 1 at 0?
At 0, it is... No, when x is 0,
Yeah.
you have minus 1. Isn't it? 6? Oh. Yeah, that's a good point. I did not go into that step first. Yeah, thank you. Very clever that you said it. So I'm drawing without absolute value first. And that's kind of how I like to explain it. But yeah, good point. So 6x minus 1 has this kind of thing over here below. The moment they put absolute value on top of it, like you said, whatever is below the graph get reflected back up. So this piece goes up. For the absolute value, the floor is lava, which, no, it's not. The floor is a mirror. That's just a joke. So it reflects back like a laser up in the parts we need. And that's why it looks like so. Instead of going down, it goes up with the absolute value. So I have several areas actually. Now it all depends where they want us to find me something. And they want me to find from 0 till 10. Well, there's a tiny triangle over here. That's going to be A1. And then this huge one will be A2. And then using geometry, that's what I put it here. Geometry in fat, very fat letters. Use geometry and you find the areas. Do you need help with that? Kind of depends on your background in geometry. And don't worry if you're bad at this, most people are. But just try to make sure you become better. Don't have to get stressed too much, but make sure you're getting better. So here's my calculations. A1, I need to find, I know it's 1/2 right away, and A2 is 1/2 right away. We know that. Area of triangle, 1/2 height times base. So now, for the area number 1, I need to figure out this size. The base is 1/6. That's how I found the intersection. Here it is. And the height is 1. How do I know? I plug 0 into my function, including absolute value, and it gives me 1. So it's 1/12. A2, I need to find this distance, which is 10 minus 1/6. 10 minus 1/6. And that is 60 over 6 minus 1 over 6. And it is 59 over 6. You see? Don't use calculators. It's much better if it's exact. 59 over 6 times, and now I want to know the height. To know the height, I will plug 10 into the function over here. 60 minus 1 gives me 59. With absolute value is still 59. And those are my two areas. Because they're both above the x-axis, we keep plus sign for each, and then you add them up together. Ta-da! And I have little graphs for you how I found all those triangles. Because it's pre-calculus and even algebra, you should take time to review it. If you have troubles with that, come to office hours. We can work on this together. I'm very okay with that. So here's your two areas. 1/12 from the very first one, and then 290, 0.8 for the second one. And I just approximated, which is pretty rare for me. I usually have exact answers. And that's what they wanted to put in exam 3, one of these problems. So it's not too bad, but then you have to draw it, and you have to find the areas, and you have to figure out. So I decided that it will take way too much time. Your homework has more problems. I solved them all here. 3 minus absolute value of x. Here you go. From -3 to 3. Use symmetry when you can. Square root of 225 minus x squared. Do you know what the graph is now? So let me write down. Very interesting. Y equals square root of 225 minus x squared. Slowly, up until calculus 3, you'll be professional with geometry because you don't have a choice, to be honest. Do you know what this graph is? Intuition tells you anything? Yes? Yeah, wait. Yeah, okay, yeah. It's going to be curved, correct. More? Wait. Yeah. Circle, very correct. More? There's more comments we can add. Circle radius 15, very good point. So if I square both sides, it gives me y squared equals 225 minus x squared. And then x squared plus y squared equals 15 squared, like you said. That is a circle, like you said, centered 0, 0, for you to know, because it's not always the case. 0, 0, radius 15. Do you all agree on that? That is not the graph, though. Wait. That is not the graph. Does anyone know? Go.
It's because it has to be positive, so it's a semicircle.
It's a semicircle, and the first part was quiet, so maybe someone will explain why, because it was good. Do you know why it's a semicircle? And you people at the back, why it's not the full circle? Anyone? Yeah, why people at the back? No? Anyone knows why it's semicircle? Just rephrase it. Repeat it, what he said. Do you know? Because it was a square root, just like you said. The square root means non-negative. Positive or 0. So I cannot go below x-axis. That is not allowed. Thus, it's a positive half of the circle. Hemicircle. We're going to do hemisphere in the future. That's half of the sphere. And if you see it's minus square root, then guess what? That's a negative part of the circle. So maybe write down y equals positive 225 minus x squared. And y equals minus square root 225 minus x squared. Those are two sides of a circle, because a circle is not a function. Have you thought about that before? It doesn't pass horizontal or vertical line test. It's not one-to-one, and it's not a function. But how can we keep working with it all the time? Because we're breaking into two parts, plus and minus square root. When you glue together plus and minus square root, it becomes what we know from school. X squared plus y squared equals r squared. Moreover, for you to know, this procedure I just did is illegal. When I'm squaring both sides, I'm losing the whole domain. Domain tells me that 225 minus x squared have to be positive or 0. That's domain. Negative, the square root of negative input will not make sense. When I square both sides, it becomes beautiful. Way too good. Now x is anything. So that's when this mistake happens. You square things, you feel happy about it, and you lose the roots. Just like on exam 3. Just like on exam 3 was upsetting. The one with the minimum and maximum. You factored out x squared. Did you factor out x squared? You did. And then it was x squared times blah, 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 and set it equal to 0. And most of you did such a good job solving this to 0 and completely forgot about this side. And then there was one critical point is missing. So upsetting, because it was the easy one. Like it takes more effort to solve quadratic equation, but no, let's forget the zero crud. And I know, I was grading yesterday, I was kind of frustrated with the algebra part. Like the calculus going well, and then the algebra just, but you know, it takes no judgment at all. It takes time to build good algebraic skills. Try to be better at this. There was a question?
Yeah, I was wondering, are we going to be allowed graphic calculators
Yeah.
on our final?
Yeah. Graphing calculators. Unfortunately, no cheat sheets. I asked. I would like to allow a formula sheet. They did not allow me. So what does it say? Hemisphere in 3D. That's how it looks like. Now you know. And so I was talking about the algebra skills. They get better with time. So just make sure you keep pushing it. Don't forget those little things. Common denominator, plus minus 1 with x squared. Don't drop some stuff suddenly, and so on. So that is important. Finally, I wanted to tell you that right now my Calculus 2 students are almost ready to get the final exam online. And we just had office hours yesterday before the exam, and some people saying, I don't remember limits at all, and we need them. We expect people to know limits like piece of cake already. We have factorials there now, and lots of series expansions and Taylors, blah, 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 Maclaurin. And then this like the base is the knowing limits at infinity. And they say that they don't know it, they don't remember it. Yeah, it's kind of very late to catch up on that. So you should know that you should retake this class if you did not learn well some very important materials. And that's good. I would rather prefer people to take the class than go and fail the next one, right? That's waste of time, waste of effort and money. While I was scrolling other examples, you will have in your homework. I solved these examples. They're pretty challenging. I will tell you that the idea is many people in this class, even not the one who are present right now, will become engineers and physicists and aerospace engineers, biologists. They will do some mistake that might cost someone's life. This bridge in Florida collapsed a couple years ago, and people were on the bridge, and it collapsed on the highway, I think, and stuff. And we all were discussing in the math department. I hope that's not me passing some student by 0.5 points of the passing grade. And the plane failed partially because of the computer science mistake, Boeing Max. And there's so many examples on that. So kind of it's very important not to slack on this. You don't want your dentist to skip classes. I have a dentist friend, and I told her, you are so responsible, I can trust you my teeth in the future. She doesn't skip anything, and she's very hardworking. And that's the mindset you should have. Are you ready to be that person? So kind of that's the idea. Algebra is part of this requirement. I think those are all examples. So just keep pushing, even if you're not good enough right now, you will be good enough later. I don't even have doubts on that. Just keep working hard on this. In my point of view, it's very easy. I already see you passing Calculus 3, all of you. I already see that in my mind. So I don't see any problem in this. You just need to either take it again or catch up or continue to do whatever you do. So there's no even pressure in my mind. I don't even see what's the problem. Just keep going. No matter how many times you need to do it, you will do it. It's fine. Calculus 3, you pass it, DFQs, algebra, whatever you take, discrete math, data science, and you get a job. Internship first and then the job. So it's going to be very fun. That's what my students right now applying for PhD program, they took my class 4 years ago. I think that's good enough. Let's have an amazing Thanksgiving. Go get fat. Come back happy. Bring some pie.